Welcome to chapter 12. We're going to do more oxidation reductions that weren't included in the part 1. Here we have an alkyne, and this is actually review, right? So we have this alkyne and we have this, what's diisoamyl? That is 5 carbons. Makes like a little Y. This is di, because of the 2. Isoamyl. An amyl is um, um, a common name. 1, 2, 3, 1, 2, 3. So it has 5 carbons. So make sure you get the 5 carbons. 1, 2, 3, 4, 5. I think it's something like this. You don't have to know this, but what I do want you to see is that this sometimes is R2BH. Because you have an aldehyde, it's to tame down the boron with just 1 hydrogen. And so this makes an enol. So let's make an enol from an alkyne. And it's the least substituted enol. And then you know the enols tautomerize. And then I just do my tautomerization like this. And then you can see that that makes an aldehyde. Make sure we have 2 carbons, 2 carbons, 2 carbons. So this makes an aldehyde. And so you can see that B is the correct answer. We're going to learn other ways to make aldehydes. This is the only way you know right now to make an aldehyde. We're going to see that you can take an alcohol. This is your primary alcohol. And you're going to see that you can add PCC, which pyridinium chlorochromate, which was introduced to you. You can just write PCC. That was introduced to you in the previous ones, and I told you it stops. It's a reagent that oxidizes. It's an oxidizing reagent that stops at the aldehyde. And the POGA will also show you that. But those are the only 2 ways that you know really how to make an aldehyde at this point. This slide you've seen before, and so this kind of gives an overview of the reactions you see in chapter 12. Okay, so here, what are we doing? This is a multi-step synthesis. We're going to, that's a base, sodium amide, and we do an acid-base reaction. This is a pKa of 25, and when we make this alkynide, so alkyne-ide, then this hydrogen that gets picked up by the nitrogen makes NH3. That's your conjugate acid. We know that that's a pK of 35. So 25 to 35, it's going 10 zeros to the alkynide. And then you have an SN2 reaction. And this is how you do a homologation, which means increases the number of carbons in your compound. So there's carbon, carbon, 1, 2, and then we're going to add these carbons here, which is 1, 2. So we have added 2 carbons. And then our next reagent is mercury sulfate and sulfuric acid. We have an alkyne that's going to make an enol. And regiochemistry, you might get both enols, but for our purposes, we're going to do this one because that is what we see as an option. And so this is going to tautomerize 1, 2, and then we have 1, 2 carbons here. Always count your carbons. There's your ketone. So B is your answer. Okay, so multi-step synthesis. How do you go from an alkyne to a tetrasubstituted carbon? Well, first of all, you got to see how many carbons you got. 1, 2, 3, 1, 2, 3. So we need to add 2 more carbons. So you're going to need sodium hydride works. Sodium hydride is a strong base that can deprotonate to give you your alkynide. And then you can react that with an SN2 reaction, right? And then that gives you this triple bond here, and then you got this carbon, and you got that carbon. So now we have 1, 2, 3, 4, 1, 2, 3, 1, 2, 1, oh, 1, 2, 3, 4, 5. So we got 5 carbons. And then you remember if you have 2 equivalents of HCl, what's that going to be? You're going to get hydrogen here and hydrogen there, and then you get the geminal chlorine. So 1, 2, 3, 4, 5. That's what you would get for this one. The tetra substituted, you're going to get your product here. So B is your answer. Okay, how do you go here? You got alkyne, and this is going to be your alkyne. Okay. So what's added? This group is added. You do 1 equivalent, so you just make 1 of these, sodium hydride. So remember, pK of this is 25. When you make this negative alkynide, then that gives you hydrogen gas, right? Hydrogen gas, pKa of this conjugate acid is 35. So this is how you make your alkynide carbon. And then that is going to have to do, and so these are all good, SN2 here. Not ideal because you would have to compete with maybe elimination, but this is pretty linear and strong, so I think that would be good. What is your product then? This is a carbon, there's a carbon. 1, 2, 3. All right, so this is the precursor after these. And then how do you get an aldehyde? So hopefully you know that this would be how to get an aldehyde through the enol. So A would be your answer. What would this one give you? This would give you a ketone, and this would give you an alkane. So be able to do all of those. So reductions of alkynes, this is, you can go all the way to the alkane, which you know how to do that. That's catalytic hydrogenation. And that's just like hydrogen gas and like palladium on carbon. You cannot stop it, okay? You don't have to do 2 equivalents. That's where it will go, to the alkane. But how do you get syn? You want syn, and you want to stop at this alkene. Then we're going to have to poison this. So this is still hydrogen gas, but you poison the palladium on carbon. So that is called Lindlar's catalyst. And so you're going to do Lindlar's catalyst to stop at the syn addition, and to go all the way to the trans. So if you want transalkene, so you want to stop at the alkene, you're going to have to use sodium metal in ammonia liquid. Now keep in mind, this is not sodium amide. And so if you do that, that's going to be wrong. That's a base. This is an electron, we call it an electron reduction reaction. And then the source of the hydrogen here is actually from the ammonia. But that gives you trans. You do need to know these 3 reduction reactions. These are special because they can stop at the alkene. And that is special. So catalytic hydrogenation, we've already talked about this. Hydrogen on palladium will go all the way to the alkane. So alkyne, functional group transformation to an alkane. Um, so if you want to go to the cis alkene, you use Lindlar's catalyst. This is basically, this is quinoline. You don't have to know all this. You can just write Lindlar, but it's quinoline and palladium on calcium carbonate. So it's a poisoned palladium. So you poison the palladium with lead 2 acetate and quinoline. It's poisoned. And that way it'll add only one equivalent of hydrogen gas. And so you get the cis. It's the only way you can get a cis alkene from an alkyne. This is a metal reduction. You take metal. I've done this actually. It's really fun. One of my funnest reactions. You put this metal. Sodium metal is like this gray silver. It's almost like butter. And you put that sodium in there. Just a little. You slide it off with like a little spatula. It's really easy. Now it's in oil because it could catch fire. Okay. And so then this is your reaction flask. And then ammonia liquid is you have to get a tank of gas, ammonia gas, NH3, and then you run a needle through here, your septum, and you have to cool this down. So then you have this in a Dewar flask, and you have it cooled like minus 78 degrees Celsius, and then you can see this ammonia is clear. Okay, so it's clear, and you can see it running down the sides of your flask. But then when it hits the sodium, it turns this like UK bright blue, okay? And what that is that's a single electron. And that's the color of a single electron. And it's really beautiful. And that's how you know you got your single electron. And then what you can do is then you can syringe in your alkyne. Then you would syringe in your alkyne, and then it would give the trans alkene. I'm going to show you the mechanism, but you don't need to know the mechanisms for these oxidation reductions. You do need to show that this is trans. So just make sure that I know that that's trans versus cis. So this is the dissolving metal reduction. And so you see that free electron there, it adds one electron. So since it's adding one electron, you get a fishhook arrow. Now, so one electron's adding to this carbon, but these two electrons are going over to this carbon, and that's why it's a double-headed arrow. And there's your negative. And anytime you get that, then it'll go and pick up the hydrogen from the ammonia. And then your ammonia generates NH2. Then you get another electron that adds from the solution, so your half arrow. When you get two electrons, it becomes a negative charge, and then it can go and take another hydrogen. And so that's how you get a trans, because these electrons repel each other. You see this radical anion? This is a new intermediate. Those electrons want to be as far away from each other as possible, and that's why you get the trans addition. Like I said, you don't have to know this mechanism, but it might be nice for you to take some time to look at it so you know it's different, and it gives you the trans alkene. These are the dissolving metal reactions. You're going to get the more stable vinyl carbon anion when they're further away from each other. So these are your three reactions for reductions of alkynes. Catalytic hydrogenation gives you an alkane. Excuse me. Lindlar's catalyst is a poisoned palladium on carbon. It's going to give you the cis alkene. And this is your metal sodium in liquid ammonia. And that gives you the trans alkene. So here, what do you have? You have the cis. So this is cis alkene. This is an alkyne. So you should know that that's Lindlar's catalyst. Okay, so then we're still talking about alkynes. We did alkenes. So do you remember alkenes? Like, so if you had an alkene and you did ozone, we did ozone, and then we did DMS. Okay, so then we did the line there, and we just did, okay, let's put in an oxygen there, and then an oxygen there. So we got a ketone and an aldehyde. Ketone and aldehyde. That was ozonolysis. That's of alkenes. Okay, well, what about alkynes? Well, alkynes, you have two double bonds, so you're going to add two oxygens. So you got to add two oxygens because you have two pi bonds. So you see here, when you add the two oxygens, you're going to make a carboxylic acid. If you have a terminal alkyne where you have a hydrogen here, it's going to go all the way to the carboxylic acid. It's going to get fully oxidized. Whereas ozonolysis, you only add one oxygen, so you can keep the aldehyde. You cannot have an aldehyde for an alkyne. It's going to go all the way, a terminal will go to a carboxylic acid. So here you have an alkyne, an ozone, and this is going to be a carboxylic acid. So you got two carbons here. And then this is 1, 2, 3 carbons, and it's going to be a carboxylic acid. So you get carboxylic acids. Here, this will be a carboxylic acid, that carbon there. But this one, since it's a terminal alkyne, will go all the way to carbon dioxide. Okay, so this is an alkene. So an alkene, we just add one. We just add one oxygen. So what I would do is I would keep this kind of the same. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then this is a ketone and a ketone. And then count how many you have. This is on the 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And they're both ketones. So A is your answer. Okay, so what about here? What's our starting material? Well, you have carboxylic acid and a carbon dioxide. So you have these carbons here, and then this carbon would have to be a triple bond to this carbon. So this would be a terminal alkyne. So there's that carbon, there's that carbon, and then you have these three. So C is your answer. These make aldehydes and ketones, so your starting material needs to be an alkene. And the alkene here will be this, and then this would be the alkene, and you see that's a ketone. So you need to have a tri-substituted alkene. Do we have a tri-substituted alkene? I don't see it. This would be an aldehyde and an aldehyde. So that's not it. This is not going to be that because that would be carboxylic acid. This is also an aldehyde, So I'm going to say there's no correct answer on this one because this would be this. So this is the actual answer. So we'll make that a fill in the blank. Okay, oxidation of alcohols. Your reagents are going to be different. Remember, they're going to be oxygen containing. I think of PCC or Jones reagents for these. And the Jones are harsher. They're going to go all the way. They cannot stop. They cannot stop. PC is mild and will stop at the aldehyde. So here you have a primary alcohol, and you can oxidize that. If you take away one of these hydrogens, you make an aldehyde. If you take away two of them, you make a carboxylic acid. So the Jones reagent is going to go to the carboxylic acid where the PCC will stop at the aldehyde. Now a secondary alcohol only has one hydrogen, so it goes to the ketone, and so it stops It doesn't go to the carboxylic acid because it only has one hydrogen. You remove a hydrogen and you increase the number of carbon-oxygen bonds in oxidation. So you could use either. You could use both PCC or you can use the Jones reagent. Tertiary alcohols have no reaction because there's no hydrogen bonded to the carbon to remove. So no reaction. They're not going to be oxidized. Okay, this is showing you chromium, potassium chromate, and sulfuric acid in water. That's the Jones reagent. And you see that you have a secondary alcohol. So there's only one hydrogen there to remove, and you make a ketone. Same thing here. And you can use either one of them, PCC, because you're not going to get any more oxidation in the ketone because there's no more hydrogens to remove on that carbon. And it's showing you the mechanism. I'm not requiring you to do this mechanism. We do a chromate ester, and you can look at that, but not required. I just expect you to be able to write starting material, products, and reagent. PCC, primary alcohols with PCC will stop at the aldehyde. We'll remove just one hydrogen and do one oxidation step. Jones reagents, however, are going to go all the way to the carboxylic acid. You cannot stop at the aldehyde. Okay, so it will go all the way to the carboxylic acid. This is the reaction mechanism of the chromate ester, and you don't need to know that. This is showing you the chromium goes from orange to green. This is what's used in a breathalyzer. So if you breathe into a breathalyzer, the active ingredient is ethanol in beer and alcohol that people drink. And this is a primary alcohol. And so this does a Jones reagent and it oxidizes it all the way to the carboxylic acid. And so this is being oxidized and then this is being reduced. The chromium is being reduced and that color is being measured. And for every oxidation state event, you get a green color. And so you can measure the green, the extent of the green color is correlated with blood alcohol level. And so that's measuring the amount of chromium 6 and chromium 3 plus in a solution. All right, so what about this? This is an epoxide opening, and here is your epoxide, and you need a hydride. So lithium hydride is a hydride, and we'll open that, and then that delivered a hydrogen from the least substituted carbon. So that would be a PCC. This is a primary alcohol. We know that this will oxidize to the aldehyde. So it stops at the aldehyde there. And you have 3 carbons. Which one's the aldehyde? This one's 4 carbons. So this is need to be corrected to CH3, CH2, CHO. So should be B because this is alcohol, alkane, but it needs to only have 3 carbons. Okay, here, let's do some retrosynthesis, folks. I can do a better retrosynthetic arrow than that. Okay, so here's our retrosynthetic arrow. This is going to come from an alkene, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This came from an alkene, and so we know to get there is MCPBA, and then we got to keep going. This came from an alkyne because we've got an alkyne here. 1, there's our alkyne. That's 3, 4, 5, 6, 7. So there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That came from an alkyne. This is cis addition, okay, because see, this is cis. So MCPBA retains stereochemistry, so this has to be cis reduction. So we're looking at Lindlar's catalyst. And then not only do you do that, you also need hydrogen gas with Lindlar's catalyst. And then how do you get here? Well, there's your 3 carbons. 1, 2, 3. That to go there, you have to use sodium hydride, apparently, as the base of choice here. And then that generates your carbon anion. And then you need to add these other carbons here. So 1, 2, 3, 4, and then a bromide there. So this is your SN2 reaction. So these all work, okay? But then you need, so that's that reaction, and then you need Lindlar's catalyst. So there's this one, and then MCPBA. So C is your answer. Which reagents would you need in order to synthesize the following compound from propyne? So propyne is this. And so you'd have to generate the sodium hydride to generate the negative, and then I think you would want an epoxide. 1, 2, 3. Could you do an epoxide? Yeah. Is that going to work there? 1, 2, 3, 4. 1, 2, 3, 4. And so then here, this is going to open from the least substituted side, and you're going to get this carbon here. It's going to go to that carbon there, and then this carbon opens up. Does that work? Actually, that doesn't open up the right way. So that's not going to work. Well, I don't think this is a great question here. I think the goal is to get an alcohol and then oxidize that, but I think we have too many carbons. So let's just skip this one. Okay, this is ozonolysis. We're making carboxylic acid, so you know the starting material needs to be an alkyne. So here we have an alkyne. So if we, this would be this carboxylic acid, and then this would be this carboxylic acid, and we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So D is the answer. This is POGL 13. This is, you don't have to do POGL 13. So I'm not going to worry about that at this point. I could just tell you, you can make this from the alcohol. So hopefully you can see that. We can just do some kind of review for this. The alcohol, so PCC would be a way to make ketones and aldehydes from alcohols. Same thing here. How would you make a ketone? You could do that from an alcohol, PCC or Jones, or you could do a ketone from an alkyne, right? So different functional groups. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And what would that be? That would be the mercury sulfate, and sulfuric acid would give you the enol that would tautomerize to a ketone. So that's another way. Here you start from an alkene, and how would you do that? You would need to add alkynes. We won't worry about this here. You'd have to go from an alkene to an alkyne. You could do electrophilic addition. So I mean, you could add HCl. You got that, and then you could add an alkyne to give you 1, 2, 3, 4. So 1, 2, 3, 1, 2, 3, 4, and then you could make sodium hydride to make an alkyne, because you need to 1, 2, 3, 4. You need to be able to increase the carbon ring, which is a common thing here, so that makes it a negative to do an SN2 reaction. And unfortunately, that would give you an alkane, but you also have the triple bond there. So let's make sure we get our number of carbons right. So 1, 2, 3, 4. 1, 2, 3, 4, and then 1, 2, 1, 2, and then you can functionalize this. So now we're not in the right vicinity here, and that's because you'd have to probably make this tetrachloride, well, dichloride, which I told you you're not going to have to do this. That's why I'm kind of reluctant here. You'd have to make an alkyne from this. So you do electrophilic addition, you would make this something like that, and then you'd have to do like sodium amide and heat to dehalogenate that, and then that's how you make an alkyne, and then that would give you your alkyne in your right place here, and then you could react that with 1, 2, 3, 4 Cl. So you would want to go the opposite way here, and that's what this really wants you to do. It's the same methodology, but then when you have a triple bond, how do you make that triple bond a halogen ketone? That's your mercury sulfate, sulfuric acid. How you get the alcohol there from the triple bond. So let's just do this and give you this precursor. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then how do you go to each one of these functional groups? If you get an alcohol, well, you could go to an alkene for each one of these. So you could use Lindlar's catalyst. Or you could do the other one, sodium in liquid ammonia, because it won't matter because you don't have cis-trans isomerization. So you could get an alkene. Once you get an alkene, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then how do you get that alcohol? Well, you can do BH3, and this is an anti-mark, hydrogen peroxide and sodium hydroxide. Once you get this primary alcohol, how do you get a carboxylic acid? Well, you could do the Jones reagent and do the oxidation. This is a ketone. Like I said, you can go straight from an alkyne with mercury sulfate, sulfuric acid. This alkene to the HBr. So HBr would get you that alkyl halide. What is the best reagent for this? This is a reduction. So carboxylic acids, and this you have a good POGL talking about this, get reduced with a really strong reducing agent, lithium aluminum hydride, whereas a ketone can get reduced with something mild like sodium borohydride, but it also will get reduced with lithium aluminum hydride. So lithium aluminum hydride will reduce a ketone to a secondary alcohol and a carboxylic acid to the primary alcohol because it goes the opposite. So you would have to use lithium aluminum hydride because sodium borohydride would not reduce the carboxylic acid. Here this is oxidation, so we're going from the secondary alcohol to a ketone. And this is important. The primary alcohol goes to an aldehyde. And only one reagent will do that, and that's PCC. Because if you use like sodium chromate, you're going to get the carboxylic acid. These are reducing agents, sodium borohydride, so they go the opposite way. And ozone is ozonolysis. And remember, ozonolysis works on alkenes and alkynes, so not alcohols. Alcohols get oxidized by PCC and Jones. And that wraps up chapter 12.